Hey there, and welcome. Think about it for a second. We've all done this. You step outside and say, wow, it's hot today, or man, it's freezing. But what does that really actually mean? How do we take a feeling, a personal sensation, and turn it into a hard number, a number that a scientist halfway across the world can understand perfectly? Well, today we're going to pull back that curtain and see exactly how we put a number on that feeling. You see, our senses are great for telling us if we need a jacket, but as scientific instruments, they're pretty terrible. What feels cold to me might be absolutely perfect for you. So the real challenge, the big question, is how do we get away from that subjective feeling and create an objective, universal measurement? How do we build that system right from scratch? All right, so here's our game plan. First, we're going to tackle the measurement challenge itself. Then, we'll walk through a super simple 3-step thermometer recipe. After that, we'll see how that one recipe works for a bunch of different tools. And finally, we'll learn to speak the language of degrees, Celsius, Fahrenheit, and Kelvin. Okay, section 1, the measurement challenge. This is all about making that huge leap from just a basic human feeling into the world of cold, hard science. So here's the bottom line. Science needs numbers. It needs data that's repeatable, that's consistent, that's reliable. My personal feeling of hot just isn't a data point. So to get there, we need to find something in the physical world that changes in a really predictable, measurable way when the temperature changes. We basically need a physical translator, something that can take that invisible energy of heat and make it visible and countable on some kind of scale. And that leads us right into section 2, the thermometer recipe. It turns out no matter how fancy or digital a thermometer looks, it's built on a surprisingly simple and honestly really elegant set of rules. So let's build one together, right now, just in our heads. Let's try a little thought experiment. Imagine I just hand you a simple glass tube filled with mercury. That's it. No markings, no numbers, nothing. You know the mercury goes up when it's warm and down when it's cold, but how do you turn that into a useful thermometer? Where would you even begin? Well, the very first thing you need is what scientists call a thermometric property. Now, that's just a fancy term for any physical thing that changes in a consistent, measurable way with temperature. For our mercury tube, that property is volume. The mercury literally expands and takes up more space as it heats up. But it could also be the pressure of a gas or even the electrical resistance of a wire. Finding a reliable property like this, that is the first and most crucial ingredient in our recipe. So once you have that property, the rest is a really simple, logical recipe. Step 1, we identify our property, in this case, the changing volume of mercury. Step 2, we need to find universal anchor points, reference points that are the same for everyone everywhere. And then step 3, once we have those anchors, we just create our scale by dividing the space between them into equal steps. It's really that straightforward. So, what makes a good fixed point? Well, we need something that's the same everywhere on Earth, under the same conditions. The answer? Good old water. The freezing point and boiling point of pure water are incredibly consistent. So we can just stick our unmarked tube in some ice water and make a mark. Then we put it in boiling water and make another mark. And just like that, boom, we have 2 rock-solid anchor points that a scientist in Tokyo or an engineer in Brazil can reproduce perfectly. Now, this simple process uncovers this really powerful universal idea. It turns out there's a direct, predictable relationship between the actual temperature and whatever property we're measuring. If the temperature changes by a certain amount, the property changes in a proportional way. Scientists write this out with a kind of master formula, where T is temperature and X is our property, like the volume of the mercury. This core relationship, this is the engine that drives every single thermometer out there. Okay, let's move on to section 3. So we have our recipe. Now let's see how different chefs, or in this case, different kinds of thermometers, use that exact same recipe, just with their own unique ingredients. So on the left, we've got our familiar old-school thermometer, which uses the changing volume of a liquid. But on the right, we have something that looks totally different, a thermocouple. It uses 2 different metals joined together that generate a tiny voltage, what's called an electromotive force, or EMF, that changes with temperature. The mechanism is completely different, but the principle, it's identical. They're both just tracking a thermometric property. And look at that. You can see how our master formula just clicks right into place. We just swap out that generic X for our new property, EMF. The core logic, the fundamental relationship, doesn't change one bit. The temperature is still directly proportional to the voltage we measure.
And it doesn't stop there. A constant volume gas thermometer, as you might guess from the name, uses the changing pressure of a gas that's trapped inside. And a platinum resistance thermometer uses, yep, you guessed it, the electrical resistance of a platinum wire, which changes super predictably with temperature.
And for the gas thermometer, it is the exact same story. The pressure of the gas just becomes our X in the formula. This is the absolute key takeaway. Whether it's expanding liquid or voltage or gas pressure, it's this universal relationship that allows us to measure temperature using all these wildly different methods. So let's just put it all together real quick. As you can see in this table, we've got 4 very different devices, and each one is tracking a totally unique physical property: volume, voltage, pressure, and resistance. It's the perfect illustration of that core idea we've been talking about. Different ingredients, but the exact same fundamental recipe. All right, on to our final section, the language of degrees. We've built the tools, we understand the principle. So now how do we create the scales, the languages that we use every day to actually talk about temperature? In science, the real true baseline is the Kelvin scale. On that scale, 0 means absolute 0, the coldest anything can possibly get. But, for telling you whether to wear a coat, that's not super practical. So the Celsius scale just shifts the starting line to a much more familiar place, the freezing point of water. It's the exact same scale, just with a more convenient starting number for our day-to-day lives. And here's the famous one, converting Fahrenheit to Celsius. Yeah, it looks a bit more complex, and that's because Fahrenheit not only has a different starting point, it also uses a different size for its degrees. But really, at its heart, this formula is just a translator. It lets us switch between these 2 different languages of temperature. Now, this is a really important point to remember. Because Celsius is just a shifted version of Kelvin, the size of 1 degree is exactly the same in both. That means if the temperature goes up by 1 degree Celsius, it has also gone up by 1 Kelvin. The steps on the ladder are the same size, even if the whole ladder starts at a different place. But this all leads to one final really fascinating problem. We've seen that we can use the expansion of mercury, or gas pressure, or electrical resistance. But do all of those properties change in exactly the same way? Does mercury expand in perfect one-to-one lockstep with the change in a gas's pressure? Well, the answer is not quite. There are tiny, tiny differences. And that raises the ultimate question. With all these different tools, how do scientists create one single, truly universal scale that everyone agrees on? Well, that's a fantastic question for another time. Thanks so much for joining me.